Okay, so I'm Bjørn-Helge Mevik. I work at the University of Oslo. In this course, I'm here for the NRIS. I'm originally trained as a statistician and worked as a researcher for some years, but since 2008, I've been working in HPC at UIO and with these types of machines. So I'm going to talk about queue systems. I'm first going to say a little bit what a queue system actually is, sort of the overall concepts of what it is. Then I'm going to go into more specifics about the queue system we actually have at our clusters, namely Slurm. And I'll touch into some of these, what we call best practices, things you should do, things you shouldn't do on our clusters, and in specific, maybe also in general. And finally, I'm going to say a little bit about available job types in NRIS. Not going to say very much about that because there are quite a few job types and the clusters are quite different. So listing through all of them and saying how all of them work and how all of them should be used and so on, it's just, you can just as easily read that on the documentation page. There's nothing more to learn from that, actually. So let's charge ahead. First of all, what is a queue system? And if you find this is too low and too naive, so feel free to sort of let your mind wander, but come back when I'm finished with this slide. If you imagine that a cluster, HPC cluster, is sort of like a restaurant, like a food restaurant, where there are a number of tables that represents the compute nodes, machines, and then there are chairs at each table representing the resources on each compute node, maybe CPU or CPU core. And then all the jobs that wants to be run there are represented by customers, right? One or more customer per job, right? So what happens then is that because we can't just have people walking into restaurants and just take a table and sit down anywhere and expect that to be fine, we need somebody to order that and fix that. And that's the waiter here, the head waiter. And that is our queue system, right? So what that waiter does, and then of course the queue system, is that it lines up people in a queue, and there's typically a sign we get into the restaurant, please wait here to be seated, right? That's the queue, that's the job queue. And when there are free resources, like empty tables, then the waiter will lead those customers to that table and place them at different chairs, and then they can order and start eating food and stuff. And then that table, those chairs are busy until those people are finished, and a new set of people can arrive. That's basically at a very, very, let's say, high level what a queue system is all about. I should tell you, I didn't do this figure here. Somebody made it for an earlier course, but I thought it was so good, I like to use it. There are a few basic concepts I think that's important to know about a queue system and how it works and what it actually relates to, what it does. One is the thing of machine resources, because that's what it hands out. In our previous example, there was sort of access to chairs, and so the chairs are the other resources here. There's also, in order for the queue system to do its job, it needs to know what requirements the job has. So every time a new customer steps up to the counter, the head waiter will ask, how many people are there and how long will you be here? Are you just going to the bar, or do you need to sit down and have a dinner, right? That type of thing. All that is put into job scripts, which you probably have seen and used a long time, where the job requirements are there and also the commands that are actually being run. That is submitted to the job queue, and after some rules, following some rules, typically priority, but there could be other stuff, they are scheduled, these jobs. They're allocated to compute nodes, to resources, like people are shown to the table. And I mean, they could suddenly come along, people in the back of the queue say, hey, I have a reservation for 5 o'clock. Okay, yeah, please come. Then you go ahead of the queue because you're reserved that table. So there could be special cases, but typically it's by priority. That was the wrong way. A little bit more about machine resources. What are they? In our parlance, a compute cluster has a number of nodes. Most sane people would call that compute machines, but we, for some reason, call them compute nodes. I think it's historical reasons for long before I've started this business. So, but it's so ingrown that yeah, it's a node. Login node, a compute node. And each of these machines or nodes, they have a number of CPUs, and they have a number of RAM chips, so a number of an amount of memory accessible for jobs. And some of them might have a number of GPUs. We have machines without GPUs, and we have nodes with 2 or 4 GPUs, or maybe all of our 4. Anyway, some of them have local disks that you can use, like I was talking about the local scratch on Saga, which is quite fast and quite big. Well, not extremely big, but I mean, it's not just a couple of gigabytes, right? And there are different types of network. In our clusters, that doesn't really matter much because we typically have InfiniBand everywhere, and it's the same type and same service level there. But there might be different types of networks, and there might even be different types of shared file systems on clusters. And in addition to that, you have software licenses. NRIS doesn't have any licenses itself, but it does give access to, so people can use their own home universities licenses for at least some software, like the let's say MATLAB, for instance. So and then that has to be requested so that we don't try to start more jobs than there are free available licenses, because then the job will just crash. The job requirements is that when or how a job specifies what it actually needs. One thing is that it needs to specify what does it need, how much resources does it need? Does it need 1 GPU, 5 GPUs? Does it need 1 gigabyte of RAM? Does it need 64 gigabytes of RAM? How many CPUs does it need, and so on. But it's also about the configuration. Can you just have 16 CPUs on any available compute node, or do they have to be at the same machine, same compute node? Some programs can handle having the CPUs on many machines, like typically MPI programs, but some programs can't. They have to have all the CPUs on the same compute node. Typically, that will be threaded or multi-threaded programs. That's how the threading works. It's just a clone of the process. And they also need to specify for how long. This is very important for scheduling, for the queue system to be as efficient as possible in placing new jobs and making them start as soon as possible. Of course, asking for too short is not a good idea, because when you've spent your time, you will be stopped. So if you haven't finished, the job hasn't finished, it will be killed and you might lose your results. Finally, in NRIS, there is the concept of accounting. It's because it's been decided that every project gets a finite number of CPU hours. We'll talk more about that later. And so we need to specify where to count the resources used by this job onto that quota. Some clusters around the world don't have that. They just use like first come, first serve, or they might use some sort of fair share priorities, meaning that if you've been running a lot right now, then your jobs get lower priority and other people can run more. But we use CPU quotas in CPU hour quotas. Sorry. in NRIS. Now over to Slurm, which is the queue system we are actually using, and which is, of course, what's most interesting here. In terms of queue system, it's quite new. It was started in 2001, so it's more than 20 years, but most of all the queue systems are significantly older than that, actually. It is quite popular. Last time I checked, a couple of years ago now, I think more than half of the top 10 biggest compute clusters in the world were actually using Slurm. And there are a lot of all of them. There are several reasons, I think, why it's quite popular. One is it's free, of course. It's open source, GPL. You can just download it, install it, and run it. The company that makes it, they SkedMD, they make the money from selling support. So since it's a complex thing to run, many people then buy support to be able to fix things faster and get help getting a better configuration and solve problems. And since it's quite new, it matches modern hardware quite okay. It has the concept of multi-core CPUs and memory banks and NUMA banks, NUMA nodes, I'm sorry. It's quite fast. I do remember running SunGrid engine many years ago, and it could like take a minute every time it wanted to try and see if a job could run. So it's quite fast, and it's actively developed, and so it's possible to get new features in there, and they fix bugs continually. As some of you might have noticed, we've just upgraded to a new version of Slurm on Saga, and for most cases there shouldn't be much of a difference for you. There is one difference with SRun and the defaults for multi-threaded programs. That's the only thing I know of, at least. One thing about Slurm is that it doesn't have many different queues. If you come from other queue systems, and so the concept of having several queues for the different types of resources is quite common. In Slurm, there is only one job queue. Every job is in the same queue with a single priority. But Slurm uses other types of concepts to separate the types of jobs that you run and where they can run. It uses QoS as body of service, and it uses partitions and so on. Jobs are scheduled by priority, so the highest priority job gets scheduled first, and so on and so on and so on. Plus backfill, which is very useful. Most queue systems today have backfill, otherwise they wouldn't be very efficient. So I'm going to show a little illustration of how backfilling will work, which we'll refer back to when we look at some best practices later on. The top half of the picture here is sort of a timeline where the green line is now, and the time is the arrow to the right here. And it's sort of a node with three, a cluster with 3 nodes. Each node has 4 CPUs. And at the current time, we have 1, A, B, C, D, E, F, 6 jobs in the queue, A to F. 4 of them are running A, B, C, and D. They have been started already and are currently running on these resources. So like job C here has 2 CPUs on node 1 and 1 CPU on node 2, whereas job A has only 1 CPU on node 2. And then there are 2 pending jobs, E and F, and we assume that E has higher priority and F lower, so following the letters here. And those can't start yet, but what Slurm does is that it creates sort of a future reservation. It's not the same as a reservation where you specify on the command line when you're going to run jobs during a course, for instance, during this course, but it's sort of an internal sort of a reservation. What that means is that Slurm will never start any other job on these nodes during that time. and it won't start anything before it if it delays its job. So at some time in the future, it will then start job E on that node, and further on in the future, it will start job F on the first node. Now, if we add 2 new jobs to the queue, so it's the same queue, same time and everything, but we just added 2 more lower priority jobs, namely G and H. And both of them are quite small. G is a bit long, but it's very slim. It's just one CPU. It can start immediately. It could actually have started here because it's idle and nobody's going to have any reservation for that CPU in the future, but still, it'll by chance start here. And it's fine because it promises by its time limit to finish before the time job F is going to start. So even if that's lower priority, it's allowed to start on that CPU because the queuing system knows that at that time the job will be gone, so it will not delay job F. And the same with job H, which wouldn't be able to start immediately without backfilling. It would be able to start at that time only. It can start here, use 2 CPUs, and finish in time for job E to start. This is why jobs are killed when they reach the time limit, and if they haven't finished already, because the queue system tries to avoid delaying higher priority jobs when they have gotten a reservation. So much for backfilling, and let's talk a little bit about some specifics of Slurm that might be different from other queue systems. Well, I think all queue systems have different ways of, let's say, identify different types, different parts of a job. In Slurm, a job is the whole thing you submit, the whole job script, and when it runs everything from start to end and all the CPUs and memory it uses and all the processes it runs, that's the whole job. In addition to that, Slurm divides a job into step. So every time you run an srun or MPI run command inside a job script, or the job script runs that starts what Slurm calls a new step. And it will have its own accounting. You can see how much memory it uses, how many CPUs it's used, and so on. Those are always run in serial, one after each other. I know there are probably some advanced users that would raise their hand and say, actually, no. So there are special cases. But let's keep to the simple facts. They run serially. So one is started, it runs, and when it's finished, you start the next one. In addition, Slurm has a special job step. It's the batch script itself. So if you write a very, very simple job which doesn't use MPI or srun at all, just runs command directly in the job script, that will be one single job step. That's the whole thing. Each job step, then, each step is then divided into a task or a number of tasks. And that corresponds to the processes of MPI run or srun. Those then run in parallel. So when you start MPI run, you want all your processes to start at once, and when all of them finished, that step is over. If you're used to MPI, this is what MPI typically call ranks. So you can call them processes or tasks or ranks. Slurm will call them tasks. And I think this, if you can wrap your head around these concepts and how they're actually used in Slurm, it will make your life at a cluster in general, and especially at a Slurm cluster, much, much easier. It will make it much easier to read the output of job stats or understand warnings or error messages and stuff from the queue system, and also design how your jobs should be run. So I don't know if it's the most important slide, but it is an important slide to understand these 3 concepts of how the anatomy of a Slurm job is. I think, yeah, let me show an example of how this works. Here we have at the top here a job script, very simple one. We specify some resources, what it needs, 4 tasks, and per CPU, that means 500 megabyte per CPU, which means per 4 CPUs, for each of the 4 CPUs, and it runs for 10 minutes, or it's allowed to run for 10 minutes. It loads an MPI module, and then it runs MPI run hostname. That will start step 0. Slurm counts as many computer programs, so it counts from 0 and up. And when that's finished, the script will go on and use srun to start another step, which will be step 1. And by default, all steps will get the same number of tasks that you've specified in the job description, job requirements. But you can, at least with srun, you can with NRIS as well, but with a different switch, you can control that and override that. So in this line, we ask for only 2 steps in that task, start tasks in that step. Oh. Sorry. And if you want to see the results afterwards, you can run sact -j and then the job ID of the job once it's been submitted and run. And we see then that the first line doesn't work to mark text here. No, it doesn't. Sorry. The first line is then sort of the accounting of the whole job as a whole. So it doesn't have a step ID or anything like that. It's just a job. It's allocated 4 CPUs and it's finished and exited without any errors. And then it's the special batch step that we talked about, which sort of represent any commands in the job script that's not part of an MPI run, started with an MPI run or srun. And there is also an external job step, which we don't really have to care about at all. It's only used in the special case where you SSH into a compute node where you have a job running, because then your processes started from the SSH will be counted as part of the external job step. It's just sort of technicality there. It doesn't really, from normal practice, it doesn't really matter. You can ignore that. Then we have step 0 from the MPI run command. MPI, OpenMPI tends to call that often that step name. Whereas if you use srun, namely step 1 here, srun will take the main command and use that as the name of that step. That's about as much as I'm going to say about the Slurm job anatomy. Now over to how to specify resources in Slurm. In general, then, looking back to the base concept here, namely step and task, you will specify how many tasks you need and where you want them, and then you will specify how much resources you need per task, typically memory and things like that. So for the first part, namely how many tasks do you need, and every step how many tasks, how many processes in an MPI run or in an srun, you would use n tasks, or you can use n tasks per node and nodes. So the n tasks you would use if you don't really care where the tasks are placed. It could be 2 on one node and 3 on another node, fine for you. N tasks per node and nodes you would combine to say that I want, for instance, 3 tasks on this node and 3 tasks on the second, and so on. When you need to control more how the tasks are allocated to nodes. That's for specifying tasks. And then you go over to the other part, namely how much resources does each task need. That will be CPUs per task. So how many CPUs do you need per task? If you don't specify that, you get 1. That's the default. On a multi-threaded program with like 16 threads, you would say CPUs per task equals 16, and so on. And then you specify how much memory you need per CPU. So if a task has one CPU and you have 4 tasks, and you say 4 GB per CPU, then you will get 4 GB per CPU and 1 CPU per task and 4 tasks. So that's 4 GB times 1 times 4. You get 16 GB in total memory. But depending on how the tasks are allocated to nodes, those 4 GB can be placed, those batches of 4 GB can be placed in different places, but they will always be 4 and 4 for each CPU. So if you have a CPU on one node, and you say mem per CPU is 4 GB, you will get 4 GB on that node. It's not going to be split. For GPUs, it's quite similar. You specify how many GPUs you need, or you can specify how many GPUs per node you need to be more precise on how they are allocated. There's a warning here. I'm not sure if it's current on Saga anymore. We just upgraded Slurm, and I haven't checked if this has been fixed. But at least on the version we have on Betsy, GPUs per task doesn't work. It gives either errors or doesn't do what it's supposed to do. So be careful about that. I'd suggest not using it so far. I'm going to test if it's been fixed on Saga, that version, and then we'll upgrade on From and Betsy eventually, but it'll take some time. Finally, the final resource you need to specify is time, how long your job needs to run. And you, of course, need to specify it long enough for your job to finish, but not too much longer. It is a good practice to try and say, okay, I know my job finishes in 5 hours, but let's say 7 then, because there could be slowdowns, there could be delays and things like that. And it's a pity if your job times out just because there was a file system delay for a moment or something like that. On the other hand, don't just specify the maximum available allowed time every time, because first of all, that's gonna, if we go back to backfilling, that means that your job will never be backfilled. It'll have to wait a long time before it starts. Also, it makes it very more difficult for the queue system to be able to know when it's supposed to be able to start all the jobs. So try and figure out how much time you actually need and add a little bit. Finally, I think that's last part of the Slurm thing here. Accounting, as I mentioned earlier, you have CPU hour quotas. Well, they're not technically CPU hour quotas. For historical reasons, we still call them that, but what you actually have is a billing unit quotas. And billing hours quota, I'm sorry. And the billing units of a job is calculated based on how many CPUs it asks for, how much memory it asks for, and how many GPUs it asks for. And the details you can find in the documentation there. But basically, we typically say that if you specify ask for just the same amount of memory as there is on a compute node, you will bill your billing cost of that memory is the same as the number of CPUs on that node. And the same with GPUs. If you ask for all the GPUs on a node, the billing cost of that will be the same as if you ask for all the CPUs on that node. It doesn't work that way all the time, especially not on the big machines. but mostly that's it. But you can read the details with the explicit weights and so on this page here. You can also see it for a job if you run exact -O and then, oh, sorry, that didn't work. Use this alloc tress field. %40 here is just to make it wide enough to print all the details. And then the elapse is how long it ran. -J and your job ID. That will tell you, you will see there's a billing equals something in the output in this column here. And you can multiply that by the elapsed time, and then you have the billing hours for that job. And of course, costs will then show you how much billing hours or CPU hours you've been using so far, and also how much is running at the moment. Sorry. Running at the moment. Yeah, that was what I was going to say about Slurm specific, I think, and submitting jobs. Now for two short slides on best practices, because this is a best practices course. I tried to add name stuff in there, but so some of these things have been said already. First of all, don't specify longer time than you really need, or plus some margin there. Main reason, as I said earlier, is to make the scheduling go quicker. You could be backfilled if it's short enough or small enough. And then your job would start earlier and finish earlier, and you'd be happier. Also, the queue system would then be able to use all the resources more efficiently, so there will be less idle resources at any time, which the ones paying for the system will be happy for, and eventually you will be too, because then they can hand out more CPU hour quotas. Because if we can't use the system efficiently, we have to sort of take account of that and then add out few lower quotas, so that people actually can run what they're supposed to be running. Also, for quicker scheduling, don't ask for more resources than you need. If you're only going to run a single CPU job, single threaded CPU job, don't ask for 16 CPUs. If it is more memory that you need, then just ask for more RAM per CPU, but don't ask for more CPUs. First of all, for you will be accounted for it, but that will also waste those CPUs. Other jobs that don't need so much memory might have used those CPUs. Whereas if you ask for them, they're locked away and nobody can use them, and you're not using them. And the same with memory. Don't ask for like too much memory. Estimating how much memory a program needs is difficult. I know that. It's a ever-going challenge. In some cases, you can start with small examples and scale them up, and then see how much memory it actually uses, and then extrapolate that for the big runs. But sometimes you just have to test and see and try and fail. Actually, unfortunately, I don't know of any foolproof, easy method to find out how much memory you need. If you know your program perfectly, then you can calculate how much memory you need. But most people don't do that. So. Also, don't ask for the resources in more specialized way than you actually need. If your program is happy getting access to 16 CPUs wherever they are on the compute nodes, don't ask it for having that on a single node, because that's going to take it longer time before the job can start, unless there is very few jobs in the system at the moment. So typically that will mean lots of longer wait time for your job. On the other hand, if you do need all CPUs on a single node, then of course you have to ask for it, if you have multi-threaded job, for instance. But for NPI jobs, at least, unless there is real benefits in terms speed of getting all the tasks on the same node, don't bother asking for it. Your job will start sooner, and the queue system can use the resources more efficiently. You do have a choice then, sort of, because they specialize things. You could choose either to optimize your job for queue time, how fast you get your results after you submitted the job and until it's completed, finished, or you can optimize how quickly it will run once it actually starts. And the question is, sort of, what should you do? I would say normally I would optimize for queue time, but there are cases where you should perhaps optimize for runtime. One case is, of course, if you're very low on CPU hour quota, then maybe it's better to make sure the jobs run as fast as possible. Alternatively, you could apply for more CPU hour quota, but if that isn't an option, then yeah, don't waste CPU hours. In more general, I'll say, take a look at the current load, do an QSUM or SQ or pending, and see what's the general load on the compute cluster right now when you're going to submit the job, right? If it is a if the load is not very high, it's a lot of idle resources, then by all means just make the job run as fast as possible. It'll start anyway. Doesn't matter. If the load is high, the job queue is long, then I'd suggest go for optimizing queue time, because then you don't have to wait that long for your results to come in, which is, for many cases, what's interesting. And I said before, using N tasks then makes it easy to get scheduled quickly, and so that's optimizing for queue time, whereas N tasks per node can give shorter runtime, depending on the job, and that would be then CPU hour runtime optimization. So for the final informative slide of this, some odds and ends. Odds and ends, I'm sorry. So, as we said before, use N tasks or N tasks per node to select the number of processes to run, which is what Slurm called tasks in the step, right? So if you run srun, imp, irun, that's what you select. If you don't specify anything, you get 1, which corresponds to running 1 process. And then use CPUs per task for the number of threads for each process. So if you have a non-standard NPI run job with a single-threaded NPI job, then you don't have to specify this, because the default is 1, and you get the number of processes, 1 CPU per process. If you have, on the other hand, a single multi-threaded program, then use ntasks1 and then specify the number of threads as CPUs per task. That way you are guaranteed that all these CPUs are allocated on the same node. So if you have a single multi-threaded program, don't say ntasks equals 16, because that could give you tasks, CPUs on different nodes, and your job can only use that on one node. And then in most cases, when you have to specify memory, most on Saga, which we are on, which you're going to run on today, I understand, you have to specify memory. And on some job types, in Fram or Betsy, you also have to do that. In some times you don't. I see there's a question here from Espen. Yes.
I just saw the do not use exclusive. There is one known exception to that. So the message to the users should be, don't use it unless you explicitly know that you need to use it.
Yes, I will say that I still don't agree that that's actually needed there, but in certain cases it doesn't harm. So, but yes, don't use it unless you explicitly know that you need to use it, and that is okay. Yeah. So for memory then, I'm going to say a little bit about the exclusive afterwards. But for memory then, I recommend mostly when you do need to specify, use mem per CPU. Because then that ties you to your tasks in each step. Only use mem if you have completely specified how your steps and tasks will be allocated over the nodes, because mem will just say that it gets so much memory on every node, and if you say minus n tasks and get tasks over 5 nodes, or you get them over 1 node instead, you don't know. And just using mem will then, first of all, you don't know how much memory your job is going to get at all, because if it's on 1 node, it'll get that amount of memory. If it's on 5 nodes, it'll get 5 times that amount of memory. So unless you have specifically specified with n tasks per node and nodes, don't use mem. I prefer using mem per CPU anyway. And then, yes, the exclusive. In at least most cases, there's no need to use it. On Fram and Betsy, the normal jobs, you get whole nodes. You get whole nodes. So there's no point in there. And in some cases, if you really want to run on a whole node on Saga or on the big mem partitions and so on, there are other ways of using it. So if you do think you need to use exclusive, contact us and we'll look at it. And typically we will find other better ways of doing it, especially when with memory. When you have memory specifications, using exclusive is not a good idea. That's the last I'm gonna say. So, no, there was one more. I miscounted. Sorry, am I running out of time?
Right now we are exactly on time, but you can.
Good, good. Yeah, I wasn't going to say very much about job types anyway, because they're listed here, and there are a lot of them, and they differ from each cluster. So the normal job on Saga is not the same as a normal job on Fram. That's how the clusters are designed to, as I know talked about earlier. They're designed with focus on different types of jobs. So the normal job is that job type that they are designed to handle. All of them have something called normal, and they have the devil, which is higher priority, but limits on how much you can run and how big jobs. And it is meant for when you sit there and develop software or tests setups in your job. So it's not meant for production. It's not meant to sort of as a loophole to get a higher priority on the jobs. It's meant when you actually sit there and you cannot continue to work before you get the results from that test. That's when the devil is meant for. Some clusters have the big mem for large memory nodes. They have actual job types for the GPU nodes, and optimist and pre-proc. And as I use these job types, what they're meant for. There will be loopholes here and there, and we don't have sort of a rule set that covers every possible scenario. But try not to abuse these things, and especially not the devil. It will be discovered, and some other use will be we're very angry with you, and we won't be very happy either, and so on. So it's a little bit like Kardemomme-loven in Norway. So be nice to each other. Right? Then I'm finished.